So sorry for that to those who wasn't able to watch this one, since I'm pretty sure that some of your classmates will watch the recorded Zoom meeting. So let's just go back again, okay? Real quick, okay? So in here, uh, here's the slide one, and then the definition of the Kirchhoff's law, okay? Wherein the main definition why we have this law right here is for us to be able to solve a more complex circuit problems, okay? Like for example, the bridge resistor circuit and then the T networks. Second one is the man who found out or developed this law. So his name is Gustav Kirchhoff. So he's a German physicist. So he was able to develop this one way back 1845. Okay, and then this law right here is divided into two. We have the KCL and then the KVL. KCL is for the Kirchhoff's current law, and then KVL is for voltage law. Okay, and for the KCL, so we just have a simple rule right here. So the total current or charge entering a junction or node is exactly equal to the charge leaving the node, as it has no other place to go except to leave, as no charge is lost within the node. So just like what I mentioned a while ago, so if we have a current of say 1 ampere right here, upon passing through a node, it is still 1 amp right here, but this one is not applicable with parallel, since this one up will be divided into two, since this is a parallel. However, if this is a series circuit, so let's make this one a series circuit. Okay, there you go. So we just have a one loop. Okay, so whatever is your current right here, upon passing through this node, it is still 1 amp right here. Okay, because there is no other way that that current will go to. Okay, so that's the rule when it comes to KCL. Okay, and then for this one, here's the equation when it comes to KCL. So we just have a simple rule. If it's entering a node, we have a positive sign. If it's leaving a node, then we have a negative sign. Okay, so that is why if you are going to take a look on this one, so we have, let's say, your 1 amp right here. So that's entering, so that's positive 1 ampere. Okay, and then we have a current that is leaving this one. So this one is now equal to or minus 1, okay, or 1 amp. And then equate that one to 0. So 1 minus 1 is equal to 0. So 0 is equal to 0. Okay, or if you want, you can transpose this one on the other side. So 1 is equal to 1. Okay, so that's basically the rule of the KCL. All right, so more explanations when it comes to the KCL. So here's the initial equation wherein we have a positive sign, but of course you have to negate those leaving currents. And then here's now the simplified version of that one. Okay, so positive, 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 and then two negatives. All right, and then here's the definition of a node. So a node is just basically a function, junction. Okay, so this is a node, 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 and so on and so forth. Okay, and we now have the second law, which is the KVL, or the Kirchhoff's voltage law. So KVL, or Kirchhoff's voltage law, so this is the definition, okay, or the rule itself of this one. So in any closed loop network, the total voltage around the loop is equal to the sum of all the voltage drops within the same loop, which is also equal to 0. Okay, so meaning, let me just get this one. So if we have, let's say, let's make this one as a voltage source. So if we have, let's say 3 volts, okay, as our voltage source, and then we have 1 amp, yeah, let's say we have 1 ohm right here, and then 1 ohm, okay, and then 1 ohm. Okay, so if you're going to add those, you'll get a total current of 1 ampere. Okay, so in here, we have a voltage drop. As you guys can see, if you're going to solve this one, we have a voltage drop of 1 volt. Okay, we have another voltage drop of 1 volt. And then we have a voltage drop of 1 volt. So as it goes back right here, it is now equal to 0. Okay, so that's why if you're going to add those three, 1 volt, 1 volt, 1 volt, it is equal to your main source of voltage. Okay, so there is no way that, like for example, you have 1 volt here, and then 0.5, nabura lahat. Let's say we have 0.5 volts right here, and then 0.5 volts right here. Okay, because this is already wrong, because if you're going to add those, you now have a total of 2 volts. Okay, so there is no other way that you'll get a voltage drop of 0.5 and 0.5 right here. So all of the voltages, all of the voltage drops, okay, if you're going to sum it up, it is equal to your original value of your voltage source. Okay, so that's basically it when it comes to KVL. Okay, so for you to be able to understand this one, so let's have this equation. So VAB plus VBC plus VCD plus VBA is equal to 0. So all you need to do is get the summation of all of those voltages and then equate that one to 0. Okay, that's how simple it is. All right. So for you to be able to appreciate this equation right here and then this equation right here, so let's have an actual example later on. Okay. But before that, uh, there's one more thing that you guys need to consider, okay, when it comes to solving a, uh, let's say, Kirchhoff's law, okay, especially in KVL. So in here, you can actually have a clockwise or anti-clockwise direction. So in here, the one that we have in here is the clockwise rotation, but you can also have the other way around, the anti-clockwise or the counterclockwise, okay? So it's just that if your uh, assumption of your rotation is correct, then you will get a result of positive. Okay, that's always the case if you have the correct assumption of uh, rotation. However, if you've got the other way around, the incorrect rotation, so your answer is still correct. However, you will get a negative result. Okay, so if that happen, just make your result positive, and then reverse the uh, rotation of your first assumption. Okay, so from this into this. Okay, but if your first assumption is correct, then no need to change the polarity. Okay, or the sign of your result. Okay, because it will give you the same result. Okay, clockwise or anti-clockwise. All right, so we have here the clockwise. We call that one actually. We actually call that one conventional current. Okay, that's the technical term for that one. Okay, from left to right. And then we have the other way around, which is the anti-clockwise or the counterclockwise. We call this one electron current. Okay, because our current is flowing from the negative going back to the positive. So that's the reason why we call that one electron current. Okay, but nevertheless, let's say this is the negative way and then this is the positive way. Okay. So are we clear so far regarding with the two types of flow of current?
Yes, sir.
How about the others? So were you guys able to follow so far? Am I too fast or just fine?
Sakto lang, sir.
Okay. Okay. So I'm doing this one. I'll be fast since we have to finish two modules. Okay. And then I hope we can only have three meetings: part one, part two, and part three. But if it's not enough, then we'll be having a part four. Okay, anyway, so let's now move on to the terminologies, okay, when it comes to solving a Kirchhoff circuit law. So we have here the node, which we have already discussed a while ago, and then the path. I hope you guys are already familiar with path. Path is just a line, okay, and then branches. So this might be new to you guys, and then loop. So this might be also new to you, and then meshes. Okay, so these terms are used frequently in circuit analysis, so it is important to understand them. So here are the definitions of those terminologies. So circuit, we have already discussed that one. Path, we're already done with this one. So it's just a line or a single line. Node, we are also done with this one. But for branch, so a branch is a single or group of components such as resistors or a source of which are connected between two nodes. So for you to be able to have a branch, so it must have a component between the two nodes. Okay, so later on we'll have a diagram for this one. And then a loop is just a simple closed path. So if there's a path that will lead you from the start up to the end, and then it leads back to the starting point, we call that one loop. Okay, so in a series circuit, so of course we only have one loop, just like this one. Okay, loop number one. If we have another circuit right here, let's say another resistor, then we have another loop right here, which is now called the second loop or loop number two. Okay, so that's it for the loop. For the mesh, so this one is kind of similar with the loop. Okay, but a mesh is a single closed loop series path that does not contain any other paths. So there are no loops inside the mesh. So let me just give you a real quick example comparing a loop versus a mesh. So let's have this as circuit. Oops. Let's have this circuit right here. Let's say this is your voltage source. This is your resistor, and then another resistor right here. So just a typical circuit, okay, parallel circuit. So I did mention a while ago that this is your first loop, this is your second loop, but you can also have a loop on the outside. Okay, so that is also possible. So all in all, we have three loops. Okay, so for the mesh, we can actually also call this one as a mesh. Well, that is actually the correct definition if it doesn't have a loop inside. Okay, so this is your first loop and then your first mesh also. Okay, so I'll call this one L and then M. So a loop and then a mesh at the same time. So this is your second loop. This is also your uh, loop, and then this is also your mesh at the same time. Okay, but for the third one, so let's say we call this one your third loop. This is just a loop. Okay, we cannot call this one a mesh. Okay, we cannot call that one a mesh because it contains another loop, okay, inside of it. So in this third loop, okay, it contains this first loop and then second loop. So if you're going to take a look on the meaning of the mesh, so it is a single closed loop series. Okay, so uh, for this one, we cannot call you cannot call the third loop as a mesh. Okay, you can only call the first loop and then second loop as a mesh, but the third one, uh, not a mesh, just a loop. Okay, so are we clear with this one so far when it comes to loop versus mesh? All right,
Yes, sir.
so I hope you guys won't get confused when it comes to definition of loop versus a mesh. Okay, so here's a diagram when it comes to branch. So we have the node right here and then another node right here, and then it has a component inside. Then we can call this one as a branch. Okay, but in here we have a node, we have another node, but it doesn't have a component between it, so we cannot call this one as a branch. Okay, so we can only call it as a branch if it's between, or if there is a component between that two nodes. Like for example, this one, another node, and then it has a component inside of it, and that is also a branch. Okay, so this is also a branch. This is also a branch, but for this one, this is not a branch. Okay, the same with this one. This is not a branch. This is not also a branch. Okay, this is not also a branch. Okay, so are we clear so far regarding with branch? So it's very straightforward. So I guess uh, you'll be able to understand this one real quick. So clear or no when it comes to branch? What about the others? All right. So 2 out of 12. Okay, so I hope the others are also were able to get this one when it comes to branch. So here's more explanations when it comes to node and then a branch. Okay, so this is a branch AE, okay, or EA. AB is also a branch. Okay, from A going to B. BD is also a branch. Okay, B going to D. Okay, so you can also have two components actually. Okay, as long as it has a components inside of that or between that nodes. Okay, B going to D. Okay, so it passed through these 2 ohms and then 4 ohms. So that's also considered as a branch. Okay, and so on and so forth. Okay, so take note this one. This is not a branch, EB. Okay, because it doesn't have a component between it. And then for the loop, so we have here AB. C, D, and then A. So this is the loop. We could say that this is your loop one. We can actually have a loop right here, another loop right here, and then another loop right here, and then another loop for the outside part. Okay, so those are the loops. So question: how many loops we can form in here in this given circuit? Is it three? Is it four? Is it five? Is it six? How many loops?
6, sir.
Six. Who says six? How about five? How about four?
Four, sir.
Oh, what about the others? So six, four. Ayun, finally. So the correct answer is five. Okay. So if you guys are going to take a look on this one, oops, what happened? So you can have a loop right here, first loop, second loop, third loop, fourth loop, and then fifth loop on the outer side. Okay, so that's why we have five loops. How about mesh? How many mesh do we have in here? Hello, hello. How many mesh? So we have five loops in total. But how about mesh? How many? Okay. So the correct answer is four. So very obvious. As long as it doesn't have a path inside it or another, a closed loop path, then that is already a mesh. So this is one mesh, another mesh, and then another mesh. So all in all, we have four meshes. But for this one, we cannot consider this one as a mesh because it contains those loops right here. Okay. Okay, so that's it for the definition of another definition for branches and then loops. Okay, so just note that components are said to be connected together in series if they have the same current. Okay, but for the other one, you could say that they are in parallel if they have the same voltage applied across them. Okay, so again, just reminding you guys the basic rules of electrical circuit, the Ohm's law. Okay, so another example of typical circuit. Okay, so loop, another loop right here. So your nodes, and then a branch right here, another branch, another branch, another branch, another branch, and then another branch. Okay, so let's have a example. Okay, with this one. Uh, but before that, since we don't have enough time anymore, so we will just continue this example on the part two. Okay, so goodbye for now, and see you guys later.
Yes, sir.
Okay, sige. Goodbye.